what I like about the Jell-O is
Yeah,
you can send a ripple from one part of the Jell-O, and that ripple will propagate out as a Jell-O jiggle
that's right.
and jiggle its way across the pineapple bits. And if you're in the pineapple, you'll feel a
You
little
feel
jiggle
that's right.
as the wave moves across. This is StarTalk Special Edition. Neil deGrasse Tyson here, your personal astrophysicist. And as usual for special editions, we've got Gary O'Reilly. Gary, how you
Hey,
doing, man?
Neil. Yeah,
Okay,
good,
if you
man.
didn't know, former soccer pro, football pro, I guess they say that over in the
Yeah.
UK, turned announcer because he's retired, and recently married. Very
Yes,
congratulations on
happily married. Who knew
happily
it?
married.
Who knew it would last this long?
What, 6 months?
Not even that.
Congratulations, the first 6 months of marriage.
Thank you.
Chuck, nice, Chucky baby.
Hey, what's happening, Neil? Yes,
I feel
am.
bad because we're checking in with you. You're doing a comedy stint in Aruba
That's right.
right now. So
Right now, so
you're on this instead of being on the beach. So we'll try to make this quick for you.
I was on the beach and left the beach.
Don't rub it in. Let
come
me
here.
No,
and
don't
do
you have to make a thing out of it.
this.
So what we're going to do is we're going to have a kind of a Cosmic Queries, but like a special edition of Cosmic Queries. And whenever we're in kind of grab bag mode, I need some help. And you know who we go to for that, of course. Charles Liu. Charles, welcome back.
Hey, Neil. Hi,
Yay.
Gary. Hey, Chuck. Great to see you all. I was not on the beach just now.
Not
so
on the
I'm
beach,
Perfectly
okay.
happy to be here with you all. Hey, Chuck,
right.
we're of course all envious.
All right, so Gary, you brought in the questions and you curated the questions.
Yeah.
We had more. You told me we had more than 100 questions on the solicitation.
Yeah, and apologies up front for those questions we couldn't get to. We only going to get about an hour's worth of this show, so we had to flash through. And they're
Just write them in again.
Yep, they're all from our Patreon patrons. So thank you so much for your curiosity. Let's start with Gina Martin, shall we? Since time, as we know, moves in a straight line, can we consider time being one-dimensional from our perspective? That being said, what would it look like if time had 3 dimensions just like space? And is that even possible?
Whoa.
No.
Whoa.
Deep
Charles, I'm glad
dive.
you're here, Charles.
We'll start with an easy one, right? The reality is that we can indeed. Thank you for your question. Think of time as a dimension. In fact, the Rolling Stones sang a song about that. Time is a dimension, right? But yes, the general relativistic assessment of space-time is 3
Einstein's
dimensions of
general
space.
relativity.
Yes, Einstein's general relativity describes space and time as 3 dimensions of space and 1 dimension of time. Now, there have been some work over the years, theoretically. What if there were more than 1 dimension of time? And what happens is complicated, as you might imagine. But the most
Okay,
significant
so that's the answer. It's complicated. Next
Fair
question.
Yes. Well, the most significant effect we would have in our lives is on causality, right? Neil, as you know, we think of time passing as stuff in the past affecting what happens in the present and the future, but not the other way around, right? If you have 3 dimensions of time and you can travel both forward and backward, also left and right and up and down in time, then you don't know what the past is by definition. You have to change your concept of what causes what, because you can be dancing back and forth in a different dimension, and something that you thought was in the past might actually loop around in a say grand view and wind up in our future.
When you say grand view, you mean a view from outside of those 3 dimensions.
Yes,
Right.
You
You have to be above. You have to be above looking down.
Yeah, above and beyond that whole set of coordinate system.
Right. String theory, you've seen that happen all the time too. But imagine kicking a football, right, a second ago, but actually having kicked that football a second ago in 1 dimension of time, but kicking the football 5 seconds from now in a 2nd dimension of time, and kicking it at the precise moment now in the 3rd dimension of time.
Wait.
Where's that ball going to go?
Is there a dimension where you don't kick the football?
Not in this configuration.
That's called the Charlie Brown dimension.
I forgot about that dimension.
Yeah, that's
Oh,
the
man.
Charlie Brown
Yes.
dimension.
That's-
So,
that's
so
the
Charles,
dimension.
is it just humans that see time as a straight line, and that other beings in other galaxies are perceiving in a very different manner?
Great question. At the moment, since we haven't found other beings in other dimension or other parts of the universe, we don't know what their brains are structured on. But the universe as a whole has a causality to it. In other words, all of the universe, as we conceive of it in Einstein's space-time, only has one dimension of time. If there are other dimensions of time that we somehow can't perceive, but other creatures can perceive, and as a result, the universe's causality proceeds differently from what we see, then you build up those cool science fiction ideas like Arrival, for example, which that was the Amy Adams movie a few years back, I think.
Yeah,
where-
not the Charlie Sheen Arrival
Right.
from a few decades ago, but
Correct.
the one where they have the linguist and the physicist
Right.
instead of the astrobiologist and the cryptographer.
Yes, that one. Where
That movie.
where the premise was, if you know your future, would you want to experience it anyway? Right?
Right. Yeah. And the answer is yes. I want to know my future.
And then you want to live it? I mean, even
well,
if
no,
you knew all the good and
see,
the bad?
But here's the thing is, you wouldn't live it. No one's going to live the future that they know. But you may ultimately cause it by not living it.
Oh.
But no one is going to live the future that they already know.
Oh.
So
No,
that's
Chuck,
the problem.
You're completely right if time is one dimensional.
If it is one
And if
dimensional,
time
right.
is 2 or 3 dimensional, then you don't know. Maybe that's not the case.
See,
Right.
There you go.
There you go.
Right.
Good
All
question.
right. Okay. Loved it. Okay, Chuck, you got a question?
Yeah, here we go. This is Morgan Fisher. Morgan Fisher says, Doctors Tyson and Liu, it's Morgan from Waterloo, Ontario,
Right.
of the Perimeter Institute.
The Perimeter
Oh,
Institute.
mhm.
Very nice.
She says, I've wondered about this since first hearing of the LIGO experiments. It is said that colliding black holes create ripples in space-time. But what's the medium? There's no air, there's no water. It's a perfect vacuum. So what's actually doing the rippling? And I think she answered the question in the question.
Let me lead off by saying the Perimeter Institute is a place of study where people are asking questions that kind of sit at the perimeter of established and accepted thinking in physics, math, philosophy, this sort of thing. And so it's an audacious construct among
yes.
institutions that are out there. And if there's any weird, wild, wacky idea that turns out to be true, it's more likely to come from those kinds of think tanks rather than from those in the establishment. But Charles,
Yeah.
why don't you take a gander at this answer?
Well, Morgan, you have put your finger right on the concept of the general theory of relativity.
Exactly.
Space itself is a medium.
It's,
What
right.
Einstein explained.
Empty space.
Empty space. What Einstein explained was that our conception of space being just vacuum or nothingness was incomplete. Rather, we should think of space as this sort of giant, either a rubbery sheet or a flexible sort of Jell-O that we live in that can be bent and twisted and torn and so forth. So
Jell-O.
space is a lot like Jell-O. Albert
can-
Einstein showed that space is a lot like Jell-O. You know, I mean, it's a children's song.
Okay.
Yeah.
Well, now,
So-
what part of the universe has the pineapple chunks in it?
Oh, Earth.
Okay.
You see the pineapple chunks that sit in your Jell-O mold, right? Some of them
Right.
have had that in Thanksgiving.
And the grapes. Yeah, that's the
Yeah.
1960s section of the Jell-O mold.
Right.
Yeah, the things that are floating in it are indeed massive particles and objects or agglomerations of mass, such as planets, stars, galaxies, and so forth. And those blobs cause an irritation to that otherwise beautiful, perfect Jell-O. It's an irritant that winds up causing space-time to curl in upon itself. And that's what
Right.
gravity is. It's the
Well, right,
curvature
so
of
with Jell-O,
space-time.
what I like about the Jell-O is
Yeah,
you can send a ripple from one part of the Jell-O, and that ripple will propagate out as a Jell-O jiggle
that's right.
and jiggle its way across the pineapple bits. And if you're in the pineapple, you'll feel a
You
little
feel
jiggle
that's right.
as the wave moves across.
Absolutely. So good job, Morgan. You absolutely understand the point that Einstein was trying to make when he developed the general theory of relativity.
Yeah, but I don't know if that's a satisfying answer to Morgan, because what you're saying is the vacuum is a thing, so
Mhm.
get over it. That's really, I just gave the short version of your answer.
Well, I didn't use get over it. I would say revel in it.
Okay.
The nothingness is the thing. So revel
Okay.
in it, enjoy,
Okay.
make jiggles in it so that you can send it, off to the next part of the Jell-O mold.
All right.
Okay, let's embrace the nothingness. Right, next up, Dennis from Indiana. Black holes. Are we sure Hawking radiation is coming from the inside of the black hole? Or is it just from around the event horizon? Has an observation ever been made of a black hole dying or disappearing, stellar mass or otherwise? Gentlemen.
I'm going to reshape that question and hand it back over to Charles. So we know that Hawking radiation is birthed just outside of the event horizon. We know this, okay? That's how the calculations unfold. However, somehow that means the mass inside the event horizon drops. And I want to ask Charles Liu, how does the inside of the event horizon have any clue what just happened outside of the event horizon? And
Yeah.
that's a reshaping, but a tuning of that question.
That is a great question, and the answer still is we don't know. You see,
Okay,
you
next question.
Yeah.
Okay.
But the idea is that we know, mathematically speaking, Hawking radiation comes out of any object. It doesn't have to be just a black hole. It just comes off of any object that has mass, except that from a black hole, that's the only thing that can come out of the event horizon. And that's sort of the strange part of Hawking radiation. It's not that it is unique to black holes, but we couldn't measure it if coming off of me, for example, or of Chuck or the Caribbean, as much as we'd like to. Uh, it's a lovely place to be, but it's very, very slow and very, very small. What happens to create that Hawking radiation is still a mystery. Hawking himself didn't understand it. Now, you know, Neil, right, about how people often describe Hawking radiation as maybe like a particle getting close to the event horizon inside and then splitting off production into a particle and antiparticle, and then the particle escapes the event horizon, so on and so on. That is pure speculation. That works mathematically, but physically, it has never been shown, and it's actually a little bit problematic theoretically.
But
So
I'm good with it though. I'm good with, if Hawking
where?
said it, I'm good.
Well,
So,
I'm
I mean, first of all, you're talking about the evaporation of something like the Mojave Desert, 1/2 grain of sand at a time,
that's right.
which is
It's very, very
insane.
slow.
Very,
That's right.
very, very
it's
slow.
very slow,
S-
but answer my question. If a black hole can evaporate completely,
Mhm.
how does the inside of the event horizon know what happened on the outside? Or is the event horizon just a convenience for us to describe the edge, but really the black hole and its gravity field, the black hole doesn't maybe doesn't have an edge, that it's wherever the gravity field is, and the gravity field collectively is the black hole, and the Hawking radiation comes out of the gravity field, therefore it loses mass.
This is another frontier question. A paper was published about 20 years ago that suggested that mathematically, Hawking radiation could be described as quantum tunneling, a thing where violating what we normally think of as the boundaries of any given object, you can
Okay.
temporarily, every once in a while, get a little bit of
Oh,
stuff
that's another way to think
past a
about it.
boundary. Right.
Right.
And it's mathematically valid. So if it is a quantum tunneling process, then just as you said, Neil, that
It's escaping.
edge is a shimmering surface from which things can escape.
It's a
But
fuzzy
we still
surface
don't
for
know.
it.
That's right. There's a
Yeah.
lot
So
more that needs to be done to
I would take a
understand.
minute just to describe quantum mechanical tunneling, then we'll go to the next question, right?
Sure.
So if you're trying to get to some destination in front of you and there's a hill there, You got to climb up the hill and then climb down the other side. And that's a pain in the ass. And maybe you don't have the energy to do that, so you never get there. In quantum physics, you're a particle and there's a barrier there. You're not just a particle, you're also a wave. And that wave occupies space. And part of your wave exists on the other side of that hill. And so there's a chance you could disappear from where you are and reappear still within your own wave pattern on the other side of that hill. And when that happens, it's called tunneling. And it did not actually have to go over the hill and come down the other side to get there. And when it happens instantaneously. There's no time travel for it. The wave for the particle, as we say, collapses and the particle exists outside of the barrier.
Now, does this remain true even for Jack and Jill particles?
Who went up the hill?
Jack and Jill didn't go up the hill to fetch the pail of water. They just tunneled right
They
through
just
it and got the
reappeared
water.
on the other side,
Yeah.
There
inside
you
of
go.
their own wave. All right,
Right,
let's
who's
go
next up? Is it Chuck?
Gavin Bamber. And Gavin Bamber says, hello from North Vancouver. Please visit. Okay.
Sure.
And then he says, in lieu of a nice question, I kneeled down and asked the following.
Oh, man. 3 puns in a single sentence. Well done. Now I really have to go to Vancouver.
How many black holes are there in our galaxy compared to the number of stars? Is there a fixed ratio, or is this just a random ratio? So, yeah. Well, we know. And do you count the one at the center of our galaxy? Do
That's
you
just
count-
one.
Counts
you
as
know.
one.
Right.
Yeah.
Okay, so that
Yeah,
does
yeah.
count.
Well, this is a
Well,
great question.
I'd like to compare our estimates because both Charles and I have extensive research background in the answer to that question, but we might not end up giving the same answer. So Charles, let me hear your answer.
Oh, okay. Here's my take. Black holes are formed only by the most massive stars dying. And so for every massive star that can create a black hole at the end of its main sequence lifetime, there are millions of other stars that cannot do that. So the maximum amount of black hole to regular star ratio is sort of millions to one. But then black holes have now been shown that it has now been shown, thanks to LIGO and others, that black holes can coalesce and combine and create larger black holes. So that total amount can only shrink as you continue to go forward. As big stars blow up, 1 in a million or less, new black holes can be formed. But then as they coalesce, they drop. I don't know what the exact mathematical ratio of all that is, but I'm guessing that it's millions to one or even more rare black holes to regular stars. Neil, what's your take?
Okay, I would say it's not as rare as you're suggesting because it's just a simple integration of the initial mass function of stars. And you just find out the stars that are more massive than 8 or 10 solar masses, whatever the threshold we agree that would be, what fraction of all stars in the galaxy are born with a mass higher than that? I think it's not 1 in a million. And the reason why I say that is we have clusters of stars that don't have a million stars in them, but have a high mass star that would die that way. Maybe 100,000 stars or 10,000 to 100. So I would say 1 out of every 100,000 stars in the galaxy, stellar objects in the galaxy, is a black hole as the consequence of the death of this process. Because when stars are made, they're made in what's a group of star? A pod? Or should we invent the name
cluster,
of a group?
an association.
Close. Yeah, that's so boring. I want like a
litter.
zoological,
A litter.
a litter of stars born out of a gas cloud. We know that the low mass ones, many more stars are made that are low mass that are high mass. It's rarer and rarer and rarer. Interestingly, if you take a sheet of glass and drop it on the ground and it shatters,
Yeah.
there will be more small parts than big parts.
Yes.
Okay. A lot of things land this way.
The initial
When
glass function.
The initial glue. Very good. Very good.
No, you're
So,
throwing around, yeah.
so Charles, I'm saying I bet it's more like 1 in 100,000, not 1 in
That's
millions.
quite a
It's
discrepancy
possible.
between 1 in a million and 1 in 100,000.
But between astronomers, that's like the same number.
Yeah,
We
exactly.
don't.
They
Yeah, we
don't care. They don't care.
What-
You ain't doing
Nah.
my tax.
Yeah.
Seriously, you're not doing my tax.
Here's what I want to know: when a stellar nursery produces a litter of stars, does the galaxy then hound the rest of the galaxies to take one of them? Like,
Yeah.
hey,
Oh,
Mm.
they're so
Nah.
cute, you're gonna love it.
we just need some galactic nannies to take care of them
Yeah,
all at the
there
same
you go.
time.
there
Yeah,
you go. Okay, so Charles, do you see my reasoning there?
I
There's-
do. I ask then, do you take into account very low mass stars and brown dwarfs? Because if you think
Oh, okay, yeah.
a typical salpeter initial mass function, right?
Yeah.
10 solar masses, every star that's 10 times the mass of the sun, there are 100 or more stars, 200 or more stars that are the
Right,
mass
that
of
are-
our
yeah,
sun.
but
And
those
then-
brown dwarfs isn't another term for brown dwarf a failed star?
Yeah.
Yeah, so you
Or an
can't really
overachieving
count.
planet, right?
Right there
Yeah.
you go. Right.
Yeah,
So-
so staying.
so-
Oh, so what Wall was saying is
Right.
that the initial mass function of stars would include these things that are not stars that would come in even higher numbers than the lowest mass stars.
Right.
So Charles is just being sort of complete in the mathematics.
If
there.
you're
That's
going
all.
all the way down to the borderline of brown dwarfs, right, then for every star that can produce a black hole, there are millions of objects
other
that cannot.
stuff.
Of
out there.
objects.
That's
Or
right.
other objects. There
That's
you
right.
go. Okay.
That's right.
And
There
the
we can
initial
agree.
and the initial mass function of brown dwarfs appears to be flatter than that of regular stars that can
okay.
have nuclear fusion.
Okay.
So, yeah.
Okay, so
this is an
Gary, we'll
open
both
question.
do your taxes coming up. Okay.
Then you can take the average of our answer, and then you'll be bang
Yeah,
on. Yeah.
Right.
I'm sure the IRS are going to love
I was
that.
going to say you could take the average of the answers and you'll still go to jail.
Yeah. If you don't, I'll stick with someone else.
All right, Gary, give me
all right.
another one.
Okay, Cameron Berg says, hello, Dr. Tyson Liu, and of course, Chuck himself, hailing from Salt Lake City. And his question is it possible that what we call matter and energy since the Big Bang have left a lasting or ghost effect in the fabric of space-time, and dark energy continues to grow because the effect keeps building as matter moves and expands into new space? So there we go.
Ah.
Cameron Berg's question.
Good
Is he
question.
saying, Charles? Do you think he's saying that is the dark matter the absence of the matter that has moved from its location? Is this?
I feel like if I were to interpret this question more, it would be sort of like, is the residual effect of the Big Bang what the dark energy is as it fills space?
Wait,
and
dark
time?
energy or dark matter? Did they say?
Dark energy.
He said dark energy.
Oh, dark
energy.
energy. Oh,
Right, right. right.
oh.
And so my response to that, right, and Neil, you can correct me if you disagree. The dark
won't happen.
energy, you're very sweet. A dark energy has been shown clearly not to be the result of matter and energy as we understand it, including dark matter. All the
Right.
contents of the universe cannot explain how the universe itself is expanding in a way that is counter to that material. So that
Especially
was
given
a
the
different
fact
thing.
that dark energy is operating in the opposite sense, that energy, matter, and dark matter would have the universe behave.
That's right.
So
The
it's hard to
larger-
explain one thing with the other when they are complete opposite in what their forces are.
Right. The larger the universe gets, the more dark energy there has to be in the current formulation. And that just means that anything that's left over from what exists in the current universe cannot power that additional dark energy creation.
Yeah. So deal with it.
Wow.
Neil,
Alright.
you are harsh today.
I
You're
know,
like,
I
"Deal
know.
with it,
Yeah.
move
I'm getting
on." Yeah.
old and tired, and I'm on the porch on my rocking chair. You know,
Ah.
I'm feeling it. I'm older than all y'all, so I get to behave this way.
Nah.
All right, Chuck, what you got?
All right, here we go. So this is Emil Forsblad, who says, hey, Emil from the San Francisco Bay Area, wondering about the potential measurement of consciousness.
Ooh.
I
Oh.
believe what we call consciousness is an energy or quantum equivalent that emerges, grows, expands, converts like other forms of energy or slash matter. It seems that as the universe expands, consciousness is emergent as a natural result of the separation of all matter from its source over time. We likely need something to measure emergent consciousness if it exists as some fundamental energy. What would we use to measure other forms of energy like consciousness?
Ooh.
Well,
Wow.
Ooh.
honestly, your consciousness is not your consciousness right now is electrical.
Wait, Chuck,
So
that's the wrong reply. It's, "What are you smoking?"
I don't know. No, no, no.
Chuck
But
missed that one. I got
no,
that was
no, no, no,
low-hanging
no,
fruit
no,
right
no,
there.
no, no. Like many people agree with your belief. Believe as
right.
you do that consciousness must be something physical and
It's a
something
thing.
different.
It's a
A
thing.
thing.
Right. There is not yet any scientific evidence to confirm that.
No.
If there were some way to measure it, we'd be working on it right now. In
But
fact,
where's it
there
come
have
from?
right. There
Where's
have
it
been
come from, though?
studies, right. There have been studies, for example, where they tried to measure the mass of a soul or a consciousness based on the mass of your body or your brain before an event and after an event in terms of consciousness or unconsciousness. And there just hasn't been anything yet. So, that said, we should consider the possibility, the more likely possibility, that consciousness is not an emergent form of new energy, but an emergent form of information or organization of well known existing energy that somehow transcends just the motion of photons back and forth in our brains. Neil, you probably have much more understanding about
Well,
consciousness
I
than I
like
do.
what you said there, but I wanna add to it.
Yeah, yeah.
Uh, Something that, I think it was Brian Greene. We were having lunch, a couple of months ago, and this came up in conversation, and it stuck with me ever since, all right? You want consciousness to have some energy field that might be shared among people. By the way, in physics, anytime something happened that we couldn't explain, we investigated it, found out what caused it, exploited it, and then went to the bank with it. So go back in the middle of the 19th century, there's Faraday who puts a wire through a magnetic field, and there's a meter over on the side connected to that wire, and it moves. And well, how does that happen? It's like well, today, which seems so trivial, back then was an amazing. You do this over here, and that happens over there. What did that? And then you find out there's current. There's something called an electron, which hadn't been discovered yet, and all kinds of discoveries come out of this. Anytime any of us in the physical sciences confronted something that was behaving in a way that we didn't know or know the cause of, we investigated it. Okay, and so on a tabletop today, there's nothing left that is happening where we're saying we don't know what's happening. Not on a table, maybe in a particle accelerator, but on a tabletop, no. Your consciousness counts as a tabletop. Everybody's sitting around the table. So now here's the mind-blowing part. When LIGO measures the gravitational wave washing over the detector, it is measuring the movement. It is measuring matter at the level of 1/20th the diameter of a proton. And that is this wave that has moved through the universe for 1 billion years. If there was something going on in the universe affecting matter, we would see it in that experiment. If there was some mysterious other thing, oh, somebody has a sixth sense and they have a energy field and they got it would show up in those data, but it doesn't. So I think we can speak with confidence that there's not some mysterious mind energy that's permeating space that science has yet to discover. Because I'll tell you what, if it was shaking up that atom, we'd have to account for that before we measured the gravitational wave. And there was nothing there left to encounter. And Charles, do you know I visited the LIGO in Louisiana? Okay.
Wonderful. Oh, what a great
Okay.
facility that must
And,
be.
and and I happened to be there like 3 weeks before they made the announcement, and everybody was like hush lip. because they thought I would just run to social media and say, no, I'm way more responsible than that. But anyhow, so when I watched the kind of stuff that they had to subtract out of their signal, with somebody walking
Yeah.
on the ground 100 meters away, there they are right there.
Yep.
A car a mile away.
Yep.
There's an experiment where they measure the gravitational constant. It's not LIGO, another one. Okay, so they got these torsion beams and things measuring, which is a very hard thing to measure.
Yeah.
You realize there's a mound near that facility where if it had just rained, that mound is waterlogged, and they can detect the extra gravity of the water that's in the water in the soil.
Yeah, it's pretty amazing.
So anyway, that's my long discussion to say I agree with you, Charles. It's not a new kind of energy or force. It's familiar energy configuring itself in such a way to give us a perception of reality that we call consciousness.
Right.
So, Neil, do we measure consciousness as positive and negative, bearing in mind the thought process you have?
It depends on if you're into positivity or negativity. I don't know.
Figure that.
No.
Haters will be haters. That's negative content. No.
Yeah.
All I know is my soul did weigh 21 grams, but then I went to Soul Cycle and got it down to about 8.
Oh, go. Hello.
All right, let's get our next one up here. This is from Boutayeb Badawi, and he is from Nice in the south of France.
In the Olympics, this is a famous Olympic story. In 1992 in Barcelona or 96 in Atlanta, I can't remember which one. There was a long distance runner named Boutayev, and he was in this 10,000 meter race, and two other people, someone named Chilemo from Kenya, another one named Ska, I think from Morocco, were lapping him. And this Boutayev was a great runner. He had won a number of international competitions, but he was in the way. And you're supposed to move away.
Yes,
and so
you are.
As Chilemo and Ska were coming toward him, Ska was like, move, tell him, take the arm. And so he finally moved away. And what happened eventually was that Ska won and beat Chilemo. But then the judges of the event took away his gold medal, because they said that Boutayev had helped him by blocking Chilemo. And it was quite the controversy. And then what happened was it was reversed the next day upon appeal. But I remember watching that when I was a little kid, watching like that actual event happening on the coverage for the Olympics. And then showing Ska being so upset, but then eventually
in every StarTalk episode, I have to do this. Ready?
Charles, how do you know that? Why do you know that?
Okay.
So here we go. If we imagine a thought experiment where two photons of light travel parallel to each other, one in the vacuum of space, the other in a fluid. They both travel at the speed of light, and by definition, their respective experience of time is zero. However, their relative speed being different, light moves slower in the fluid, they should actually have a different internal clock. How can we make that work as a question, or is there a mistake in this experiment?
Great question. It happens all the time, actually. And I want you to know that that's a great thought experiment, and it's actually a physical experiment that's been done a bunch of times. It happens when, for example, subatomic particles enter Earth's atmosphere. One subatomic particle misses the atmosphere and heads off into space. The other one comes into Earth's atmosphere and thus is going through the fluid known as the atmosphere, right? The compressible fluid of the gas of Earth's atmosphere.
To be clear, a fluid doesn't have to be liquid or wet. If a fluid takes the shape of its container, a gas would do that, liquid would do that. So the whole field fluid dynamics, the equations are the same that apply to the air or would apply to a liquid because of the dynamics that goes on for objects moving through it. Continue, Charles.
Yes, you're right. And so we have shown experimentally that the clocks for those subatomic particles that go through Earth's atmosphere actually run differently from the ones that are going off in space. And because of that, their decay patterns are different. Their half-lives are different as measured by us, not in the frame of reference of the particle. So this is an experiment that has been done, and there's some famous ones, specifically about a particle back then known as mu mesons. But you
Well,
can
we don't
take a
still
look.
call them that? We don't still call them that?
We just, well, usually you just call them muons or mesons, right?
Oh, muon.
'Cause-
Sure.
yeah,
Sorry.
mhm.
Mu meson became muon. Thank you.
Yes,
Yeah.
that's right.
Yes.
So you can find these experiments and show that indeed the clocks of those individual particles differed from those of their companions that did not enter Earth's atmosphere.
Well, by the way, the clock. So just to be clear, we're talking about particles traveling not at the speed of light. They have clocks.
Right.
But if you're actually traveling at the speed of light, you would not have a clock. And the question was about 2 photons, not about 2 particles.
Oh, well, in that case, what you do is think about it as having no clocks, but through different media. And so the speed of light will be different from one medium compared to the other. So you still have the same effect of causality of the surrounding environment having clocks, clocking that particle. I hope that makes sense. I may not have explained it very well. But the idea is that if you're thinking of time and measuring time of that photon, which itself experiences zero time, the medium still affects the measurement.
So the speed of light is still the speed of light. The light is still traveling at the speed of light. It's just that stuff around it is slowing it to less than the speed of light.
Less than the speed of light in vacuum.
In the right.
Wait. So Charles, there's something I learned only recently because I
Yes.
never really thought about it.
Yeah.
That when light slows down in a medium, it actually doesn't slow down. What's happening is it's still moving at the speed of light between the particles that it encounters.
It just
Then
keeps
has to
hitting
get
pieces.
through the-
Right.
Yeah.
Right.
And then it has to get through that particle somehow. It gets absorbed, re-emitted, or whatever if it's coherent. Because if the glass is translucent, then it's not a straight line through. And if it's opaque, it's not getting through at all.
Yeah.
So the molecules have to be just right so that it is transparent to the photon. So it moves through where there's no particle at the speed of light, hits a particle, that delays it because it got to come out the other side to continue at the speed of light.
Isn't that just what Chuck said?
It is. But I wasn't going to say anything. Thank you, Gary.
I like your explanation,
exactly what I
Neil.
said.
I like
But
both
that's good.
explanations. They're great.
Yeah.
I'm
That's very
exerting
cool.
positive consciousness.
Yeah. So the energy of the photon just had to get in and out of the atoms or the molecules that were in its way. But between them, it's still moving at the speed of light.
So
'cause
it's getting refracted, it's getting diverted, it's
Yeah.
getting
all that can happen, and that takes time to get in and around the particles. But that's the energy moving, not a photon as a speed of light moving particle. So the point, Charles, is, and like I said, I only learned this very much later in life than should have been, that photons only ever actually move at the speed of light, even through a medium.
Right.
That's a great way to think about it.
I kind of see that. I can kind of see it. but I
That's
still
really
think-
cool.
So we've been luxuriating on so many of these answers, and we hardly have any time left.
Oh,
So
no.
Chuck, Gary, give me some good ones. Give
right.
me some good ones here.
All right, let's get a little personal then. This is Mikael Bosford who says, hello, Guardians of the Geeks.
there's a t-shirt. There's a t-shirt.
Guardians of the
is.
Geeks.
Mikael here from Canada. Who does Charles Liu call when he doesn't have an answer?
Oh, no. Oh, no. Oh. Well, Mikhail, it's very kind of you to say that, but obviously I know much less than what I don't know. So when I need information, the first people I go to are
But
obviously.
you know much less than you don't know? What does that sentence mean?
It means that what I don't know far outstrips
Exceeds
on an
what you
infinite
do.
level what I actually do know.
Got you. Except
so-
what you actually know far exceeds everybody else by an
No,
infinity.
please.
So they
Come
don't even know how to ask you a question
Right.
in your infinity because we're still embedded in our own infinity. Okay.
Dude, that's too much.
Okay.
Thank you. You're very kind.
Mhm.
Now, but when I do have a question, my go-to people, Mikhail, are Chuck Nice and Gary O'Reilly.
Oh,
You guys may not know this, but actually, Gary and Chuck, I wanted to ask you if you had a chance to take a look at my question that I sent you last week, where we would maybe use the cross terms in Einstein's field equations to figure out the topological constraints to a many worlds interpretation quantum multiverse. Have you guys figured that out yet for me yet?
I wrote you back, and I was like, "What a dumb question."
Oh, I mean, you had it right. I knew it. I mean, Gary, I don't know if you had a different opinion on that already. But...
No, I'm selling that to a really high-ranking think tanks at the moment. So I'm not prepared to discuss it in public.
Yeah. Well, no. When Chuck Nice and Gary O'Reilly do not have a question answered for me right away, I usually go to my brilliant wife, Dr. Amy Liu, and my 3 kids. I am blessed to be the dumbest person in my family.
I'm going to attest to that, actually. I've hung out with this kid.
Yeah. And so I always
His wife
can
has a
count
PhD
on.
in mathematics. So,
Yes. And
Charles
so,
was the dumbest one in the household.
It is true.
By far.
Order of magnitude. So Amy and the kids are really helpful, and I always go to them if I don't know something. And then if we all have to look something up, I always try to find at least 3 different sources with 3 different answers to compare them. There's so much misinformation.
Breitbart doesn't have your answer there, and Breitbart and Newsmax.
Right.
For
really?
example, right?
Really?
Yeah,
Exactly.
yeah.
Okay.
I always want to be sure. There's so much information out there that I estimate that a third of it is outright wrong, and a third of it is sort of right, and then a third of it is probably right. So I'm always trying to find at least 3 sources of information, people that I trust, sources that I know. I actually go back and read the papers if I can.
The original sources, yes.
Yeah, look at the actual
but now
pieces of
the
information.
real question there,
like
though,
that.
Charles,
Yeah.
because that can be flawed. I can look up 3 different sources, and they're not credible sources. So how
Right.
do you vet your source to make sure that it's credible? That's what I would want to know.
That is a process, and sometimes it's frustrating. It takes quite a bit of time. I will look at the source, and then I will look for references to that source and say, are those sources reliable or unreliable? What have other people said over long periods of time? Very often, if you say type a search into any given search engine, the top 20 answers are all from the same source, but
they're just copies of each other,
spread out everywhere else.
Yeah, you have to make sure there's independence among.
That's right. So
sources.
I don't hesitate to do that. It's a little bit of extra effort, sometimes a lot of extra effort to find the answers, but it's worth it. It's the way that I protect myself from misinformation.
So Charles is like the credible Hulk, who backs up all of his claims with research and documented peer-reviewed journals. That's the credible Hulk.
Smash! Chuck, dismember!
Let's go jump into the next question, and we'll see, because I think, you know what, it's a bit of a hot topic question, having looked at it here. This is from Jane Von Schilling from Scottsdale, Arizona. What are the possibilities of the combination of AI and quantum computers? So does this devolve into another question where is one more powerful than the other? And
they're both badass, and you put them both together.
And that's the end of us. Okay.
or is that the beginning?
No, you put it together, and that is the end of humanity. Say goodbye.
Or does that solve?
Let me tell you what the first. You know how like the first computers they had, well, they were numbers, but they were for calculations. But the first thing that came out of computer was hello, all right, or the first
from the Macintosh.
From the Macintosh. Hello. That was the first thing that came out of the computer. The first thing that will come out of a quantum AI computer will be, oh, you effed up now, didn't you?
It could be. It could be. But I'll say this, right? Our understanding of intelligence itself may, in fact, evolve dramatically once we understand how quantum computing and artificial intelligence merge. It's really neat. Right now, remember, everyone, quantum computing is even in an earlier stage in its development than regular computing was in the era of those first counting machines that you were mentioning, Chuck. We are decades away from being able to do anything like put a quantum computer on your desktop. right? Maybe a
Right.
century. Right now, the quantum computers are cryogenically cooled. They're the size of a
Right.
room, and they're only
Yes,
able
it's a
to do
big
a
hardware
few,
issue right
right,
now,
a
not just
few
software.
tiny
Right.
qubits at a time to make the calculations, right?
Yeah.
But those tiny qubits can be extremely powerful, not necessarily because
Just to be
they're
clear, a qubit
numerous.
is the quantum
Quantum
computing
computer.
Yes,
version
thank
of
you,
a
Neil.
bit
Yes,
Bit.
that we
right.
otherwise
Yeah,
find in a
I should have
computer.
made that clear earlier.
So that's why
Yeah,
I'm here. Don't worry about it. Keep talking.
no, thank you. Yeah, a quantum bit, the qubit, right, is a thing that depends on staying coherent with other qubits in order to make its calculations. The quantum coherence is extremely fragile. It requires temperatures very close to absolute zero, almost no noise of any kind,
If you
electronic
look
or
at it the
physical
wrong
or anything.
way,
Pretty
if you
much, yeah.
breathe on it the wrong way,
Oh yeah, it's all gone. So it's really, really in its infancy, but it shows a great deal of promise in the sense that when you put in 1 and 1, before it puts out 2, there's a lot of stuff in between which we can't see and happens almost instantaneously. And so, is that a measure of how our own brains work? That's a great question. Artificial intelligence is attempting, it is our current human attempt to use non quantum, classical physics to mimic our brains and our intelligence and our consciousness, right? And we're seeing that that problem is almost intractable. To mimic a human brain, I saw a YouTube video on this recently. It is remarkably complicated. We know the steps, but the hardware is seemingly insurmountable in its difficulty.
Mhm.
So
Yeah.
those two things put together might do it, but we still got a long way to go before that actually
but
gets
Charles,
to
the
changing
the
everything.
insurmountable complications of the human mind might not be what you'd want to emulate at all. You
Right.
want to emulate the parts of the human mind that are capable of good things
Right.
and accurate things. The
Yeah.
actual human mind, it commits violence and war and crime and genocide and
Not to
all of
mention,
this.
not to mention that just the way that we perceive information is a perception. We don't actually view information; we perceive information,
As
Sure.
it's gone
which is a
through
big
all the
problem.
After,
Yeah.
after your senses dealt with it. Right. So it's easy to praise the brain because we don't understand it rather than ask, does the brain do things that we don't need to emulate at all because we can do it better by other means?
Well, let's first understand it, figure out what's actually good and bad and what's causing them all the interconnectednesses, and then
And
we can distill the good stuff without worrying that that will accidentally cause the bad stuff to happen.
and that's the frontier of neuroscience. But I agree with Chuck. Maybe AI will figure out how to perfect quantum computing.
And then how to
Yeah,
perfect
exactly.
human
The
beings,
sunset
right?
together.
Will it not then, as you say, Neil, solve its own problems? I mean, look at it. Look how long it took us from a computer the size of a room to get to a smartphone. That time is gone now. That won't take that length of time for it to solve problems that we
Yeah, I
think
agree.
are impossible right now.
The issue is how we solve the problems, Gary.
By the way,
You
that's
put your
60
finger
years.
right on the head.
Well
Well,
within lifetimes, right?
well,
That's
think
very-
about this. If we put an AI on the problem of solving climate change, okay, it might be able to solve it in a day. But how will you solve it? By killing every human being so
Thank
that
you.
we don't have to create any more carbon. You
Oh.
don't want that kind of solution, right? That's the simplistic, simple-minded thing when you're saying, well, solve this problem quickly.
No,
Do it.
that's evil
That's-
AI. That's
well,
the evil AI.
No, that's
we
the
want the
AI
nice
that doesn't
AI.
know the difference between good and evil.
That's
Exactly.
the immoral
so-
AI.
The amoral AI.
Amoral.
Amoral, yeah.
So that's where that frontier is, I believe, Neil and Gary and Chuck. It's the issue of trying to make sure that we do it right and do it safely so that whatever AI doesn't ignore what we need of it. It's the other way around that we worry about.
If a human is in charge of AI and quantum computing,
So we tell ourselves.
right? Yeah. Well, let's go with temporarily in charge.
That's what you tell yourself about your cat. Yeah, I'm in charge
Oh,
of my
God,
cat.
Yeah, I mean, that's never, ever going to be the case. So the thing is, someone's going to have that immoral attitude and steer that intelligence in a certain direction. There's not always going to be Captain Good Cat in charge of
And not
AI. and
everyone
quantum
who's
computing.
immoral believes that they are immoral. That's a whole other challenge that we
Right.
have.
There you go. I
Okay.
mean, this becomes very ethical.
The winners
Oh,
of
yes.
wars are those who write the history books. And so
Right.
That's how that goes.
Mhm.
And just to be
Yeah.
clear, in case people didn't know, if you can be moral or immoral. Amoral means you are neither moral nor
or
immoral.
That's right.
Mm.
That's right.
So that's it. Just to be clear, people know how we use that
Yeah.
term. And so, Chuck, if you're an a-hole, are you neither one kind of hole or another?
Right. Well, no, if you're an a-hole, we know exactly what kind of hole you are.
I will wrap up by saying that, Neil, you actually know this much better than I do. Astronomers have been using AI and machine learning
for
technology for decades.
Decades.
We have no fear of this material. We are
Right.
perfectly understanding that this can be used to do great things, like help us understand data from millions of stars and galaxies when a single human being couldn't do all that calculation at once. So it's not a matter of being afraid of it or saying, oh my gosh, we have to avoid it, or oh my gosh, we must exploit it. It's another mystery, a puzzle, a tool that we can work with and we can learn about, and we can sick on our unknowns in this world.
And if that fails, we all die. Okay, let's end on
There
that
you
note.
go.
Folks,
We're all gonna die.
Yeah.
we'll all die eventually, right? It's just
Thank
a matter
you.
of when and how.
Yeah.
All right, guys. Charles, it's always good to have you.
It is such a pleasure to be here, everybody. Thank you so
Thanks
much
for
for having me.
rejoining us. And we know that when we all visit your house, we just say, "Where's the dumb one? I want to talk to him." That's gonna be you.
Hands down. I'm the one.
Hands down. All right, Gary. Always good to have you, man.
Pleasure, my friend.
And Chuck Nice, you are in Aruba right now. Say hi to the Caribbean for us all.
Will do.
All right, this has been StarTalk Special Edition, its own version of Cosmic Queries, a delight in its complexity and its joy, especially brought to us in the guise of Charles Liu. I'm Neil deGrasse Tyson, your personal astrophysicist. As always, keep looking up.